Okay, so this is just to make sure we're all on the same page. You guys, who's done 324? Okay, who's not done 260? Is everybody, you haven't done 260, but a lot of you guys are software type people, right? Is that the approach we're taking? Okay. So whenever we're controlling something, we want to sort of, we have to have the desired thing and what we're actually at. We have these two states, right? The state we want to be at and the state where we're actually at. Let's start with temperature, okay? We want to control the temperature of the room. We want to hit 21 degrees. We're at 18. In order to get there, so we start by defining our error. What's our error? If we're at 18 now and we want to be at 21, our error is 3 degrees, right? So whatever the thing is, whether it's velocity or temperature or position, we've got an error thing, and that's what we're trying to minimize. We're trying to get that small as we can, or within some band or whatever, right? So usually we characterize things by a step response. Like what happens if we try to immediately go from here to there, from A to B, from 18 to 21? And after some time, usually our system will sort of settle, and we call that our steady state error value. So if we try to move these wheels by one rotation, and our system moves them by 0.95 a rotation, and it stops, and the control system goes, I'm done. Okay? No, control systems will never get exactly there. They're always going to get within some band. So there's this concept of a steady state error or a steady state value. We'll have usually often we may have overshoot depending on how much friction there is in the system, how much damping there is in the system, how much inertia there is in the system. If there's lots of inertia in the system, we're more likely to have overshoot. If there's lots of friction in the system, we're less likely to have overshoot, right? So this thing right here actually has, a lot of friction, but it also has a reasonable amount of inertia. And as you guys add more weight to that, you'll get more inertia. So mostly what we're going to talk about today is going to be, we'll start with position control, okay? Because it's a little easier than speed control, but all of the principles apply to speed control. So do you guys know what are you going to have to control in your project? Do you know? We talking position? We talking speed? Anybody? Rex?
Position.
Primarily position. Okay. And there are lots of ways, lots of information we can get to do position control. On this robot, what we're going to use today are the encoders. Does anybody want to tell me, or does anybody prepared to say, I don't know what an encoder is? Somebody say those words. I don't know what an encoder is.
I don't know what an encoder is.
But you do, so you can't say that.
You said somebody say it.
Someone who doesn't know it.
Somebody say they don't know what an encoder is. Come on.
I don't know what an encoder is.
That's the spirit. Okay. So the motors that you guys are using look like that. And we've got too many things here. Okay, so we'll pass that around, right? That's the motors. You guys have seen them on the thing, whether you've seen them off or not. On the back of that, you've got the power, right? The red and the black is what makes it go. Then you've got a connector like this that goes in the back of this. And this is the thing that's called, it talks to the encoder. Underneath this black cap, there's a magnet that spins around and some magnetic sensors. And the magnetic sensors generate a square pulse when the shaft spins. All right? And there's two of them. So we're not going to get too much into exactly how quadrature encoders work, but on this cable you'll find 4 wires, power and ground, so 5 volt and ground, and an A and a B line. And by counting when the A's go and when the B's go and when they go high and when they go low, you can keep track of how far this shaft is turned. So the first step in getting our robot here, what we'd like this robot to do initially is to drive a certain distance and stop. Okay? Now it sounds trivial, but it's not actually that trivial. It depends where you're coming from. So I've built the start of this. Who can see this? If you can't see it, you're way too far away. Now we've done the best we can to get this in here, but you can see it fine. You probably can't read this screen. So there's no point in being here unless you can read the screen. Okay? So fill up the front chairs first before any of the back chairs.
You can do control plus or control up to increase the text size?
Yep, we could do that. Control shift plus maybe? I've had somebody, yeah. Tab, previous tab, yeah. Does anybody have any ideas here? If we can increase the text size? I spent all of 466 with one student who had this new awesome computer with super lots of pixels and he couldn't change it. We couldn't. Anyway, okay. Can you guys all see that now? Okay. So I've built this out into a few steps. The first thing, what is going on here, and maybe it's worth having a look. I'll sketch it up on the board. The Arduino has special features on it called interrupts that are meant to, that are good for talking to encoders. Interrupts are special, who knows what, interrupts, yes? Interrupts, if you know what an interrupt is, hands up. Okay, lots of you don't. The interrupt will always listen to a rising pulse. Doesn't matter what else is going on. So if you have, if your Arduino is trying to do lots of other things and the wheel turns, the idea is we don't want to lose that pulse. We don't want to ignore the pulse. So it has, it's on what's called an interrupt, which is a high priority. So on this, you've got, oh, that one. So we've got our motor, and on the back of that is interrupt. Now I'm just going to draw the A and the B line on the interrupt. We're not worrying about the power and ground and all those other things. This, and we actually have two motors. So there's two A's and two B's. So we'll call this the left, and we'll call this the right. Right? The if you look at the Arduino pinouts, 18 and 19 are interrupts. So I'm going to take A to 18, and I'm going to take this A to 19. Yeah, Rex.
They actually have 4 motors.
Oh, they have 4.
They have 4, so we're talking about 1 motor on each side.
Oh, that's right. But they're chained together. So I'm actually only going to, right now, the way I've done it here is I've only hooked up one of the motors to the interrupt, even though there is actually 2 motors on the left and 2 motors on the right. I'm not worrying about the other motors because they've got that belt that connects them all. So I'm going to assume they're all doing the same thing. And that's what, on the code, you'll see we've now attached, in software, attach interrupt, digital pin to interrupt. So this handles the fact that different Arduino boards have different interrupts on different pins. So I've just said, on pin 18, there is an interrupt that will run a program called ISR left on the rising edge. So anytime pin 18 has a rising edge, there's a function called ISR left that's going to run. Right now, ISR left does something. It does count left equals count left plus 1. So it's going to take an integer called count, and it's going to increment it by 1 anytime that there's a rising edge on that thing. It's not exactly what we're going to do, but it's just an example. And then did I put anything on ISR right? Yeah, the same thing. Ultimately, this variable called count right is going to do the counting of our position. Right? It's going to represent how many ticks forward we are, how many ticks back. We don't know right now how many ticks will be in a meter, but we could figure that out. Because we can either experimentally determine it, or we can go look at the data sheet for the motor, and it'll tell us that there are 240 ticks per revolution or something like that, and then is that geared or ungeared, and we got a 40x gearbox or whatever it is. For now, we're not going to worry about it. For now, right now, what we're trying to do is, yeah, we've got the interrupts going, and then the other thing that we don't want to, I'd like to print out to the serial monitor how many ticks we're at, what our position is. I want to get some feedback on that, and I could put in my loop that I want to talk to the serial port really, really rapidly, but I didn't want to do that. So I used a library or a function called Metro, and Metro is a way to schedule events. So like a train, like the Paris Metro comes every 10 minutes. This Metro will be a function called serial Metro that runs every 250 milliseconds. So every 250 milliseconds, what I want to do is just talk to the serial port, send some data to the serial port, and then for all the rest of the time, which is a lot of the time, right? 4 times a second I'm going to do this communication. All the rest of the time, I'm going to worry about controlling my robot. And here is the if serial metro.check is equal to 1, so this is if this is true, and this is only true every 250 milliseconds, then serial print the left counter with a tab, and then the right counter, and I'm actually going to, for now, just increase the count left and count right, just for now, just to show that it's actually working. Every 200, so at 4 times a second, the left and right position should increase. Okay, so let's just leave that for now and see. So the really point of this is to make sure that we've got our serial monitor running. So, and we don't really know if our interrupts are going to run yet, but we'll check that later. Looks like it's compiling okay. Okay, and then I need to turn my serial monitor on. I have set, this is an unusual baud rate, but it's high. See serial begin 11520. I've got the baud rate the same here. If that's different, I'm just going to get gibberish, because it's not going to be receiving the things right now. So this is the left encoder and the right encoder, and they're increasing 4 times a second or something like that, or about that. Any questions on this? So we're not using the interrupts yet, but at least it compiles. We've set some things up. If I was to take, I could test the interrupts in many ways, but we'll do that in the next step. Any questions on this? You guys are very quiet. Okay. So let's look at, the next step is going to be to test the interrupts. So I've got another program here called stage 2. So what have I done differently here? I've defined 22 and 23 as inputs. Any thoughts what 22 and 23 are going to be for? Look, the code, I'll make the code available, all this stuff. We'll give it all. So 22 and 23?
Left B and right.
That's right. They're left B and right B. Now you could run these to interrupts again, but in this case I'm not going to. So this one's going to go to 22, and this one's going to 23. Now, just having a pulse on the A pin isn't enough to tell us if we're going forwards or backwards, right? We could have forwards would generate a rising pulse, backwards would generate a rising pulse. We don't know if we went forwards or backwards. The A and B are called quadrature encoders because if you think of the hands of a clock, the A will generate a rising pulse here, and the B will generate a rising pulse there. And that allows us sort of an asymmetry, a way to go forward. Now we won't get into the detail of it, but I'll show you how we do that and what the code, how we do that. So each of these interrupt service routines, ISR left and ISR right, are going to be triggered on a rising edge of that one. What we do in the interrupt service routine is this. So we have to digest this and take this really slowly, make sure we understand this. As soon as we trigger the rising edge on A, we go into here. Then we check the B. So if 18 went high, we'd go in here. Then we check the state of the B channel. If B is high, we know that we went forward. If B is low, we know we went reverse. And that's how interrupts work. That's how quadrature encoders and interrupts work. So that's all your interrupt service routine should do. Your interrupt service routine gets called at a high priority. So if you have a high priority event, what you don't want that event to be is long and tedious, right? Because it happens a lot, and it takes priority over everything else. So if you, for example, put in here a serial print or some communication protocol where you're going to send a bunch of bits back and forth to the computer over the USB, that's a disaster because it's going to mean that the whole process slows way down. And good control systems rely on rapid feedback. Get the state, change the state, get the state, stay in shape. And you can't, if that gets slowed down by doing other things, it's bad. So the interrupt service routines need to be short and snappy. No delays, no long-term communications, no potential waits, nothing. All we've done is check the state, count, and you could write count left equals plus plus or count left plus plus or whatever it is, but that's confusing sometimes. Or so it's either going to increase or it's going to decrease. Same on the right one. It's either going to increase or the decrease. All right. So we should be able to run this code now and see what happens. Any questions or anything on this? We would have defined some variables. I'm trying to think if there's anything else in here that needs to be mentioned. I have defined, I've initialized count left and count right to be 0. Let's push this out there and see. So what's going to happen to my serial port when this gets running? You're on the right. I like it that he's thinking. It's good. Right now, anything going to happen? Looks like it went. So someone's going to tell me. Nothing's happening, right? We should have a bunch of zeros. Great. Lots of zeros. Because the wheels aren't moving. I could take 18 and 19 if I really wanted to. I could take my 18 and 19s here. Where are they? This one here. This is 18. I could take 18. And I could bounce it back and forth from highs to lows. So let's see if I can do that here. Let's go from the rails. High, low, high, low, high, low. Am I getting anywhere?
Yeah, it's dropping.
Okay, cool. It's dropping, right? So I'll put this back. And it doesn't matter necessarily, whether it's yellow or green or which is where. Eventually we'll figure out all the signs and polarities. It took me like 20 minutes to get the signs and polarities right. They're not right yet, So let's see, that's still running. So if I pick up the robot here and I just drag a motor, all right. So now I've got software that can keep track of my wheel position. right? So that's all it is. It's not any, terribly more complicated than that. One thing now that I know you guys are software, you don't have to worry about this. The grub screws get loose on this pretty easily. So if you pick up your robot and you give it a wiggle like this, and there's a lot of wiggle, that's a bit more wiggle than there should be already. That means the grub screws are getting loose and the wheels are losing contact with the shaft. This one probably is still pretty snug. See how much wiggle we got in this one? Yeah, it's a little bit less. Not so bad. But you'll see that wiggling that won't change that because I'm not actually moving the motors. I've got to really, there we go. Now we get a change on the motors. All right, and if I do a reset, what's going to happen? Rex? You're not waving at me?
Good.
What's going to happen if I hit the reset button?
Should get a 0.
All goes back to 0, right? So we're going to end up, yep. Okay, so let's say that now I want to take the next step and make this robot drive for a certain number of counts, like 1,000 counts. What have I got to do?
While loop.
Yep. Well, we've got a while loop in a sense that we've got this, we've got our main loop here. This loop is our main loop here, right? This thing right now is doing its metro, and that's it. So how are we going to make this go? Rex?
Everyone can ignore me from a live data. Do you know the FRC command-based robot library?
No.
Okay. I don't know what you get for FTC, so I've got some software for the Arduino
Okay.
that will actually run a series of commands, making a very simple structure for a command, which is you have a routine that's called and it either returns true or false without saying call me again later on.
So what's an example of a basic command that I might...
So you might have a drive forward command, which will wait until is the number of ticks now that number, otherwise keep asking whether to move forward.
Okay, so do we not... So I was going to go through a sort of a basic, if the ticks are greater than... Let's say we want to get to 1,000. If the number of ticks we're at is less than 1,000, let's put positive power to the motors, and if it's less than 1,000, let's put negative power to the motors. So that's a way we could drive forward. Is that too low a level, or should we do that anyway?
Do it anyway.
Okay.
Because there's also libraries for doing quadrature encoders and things
Yeah,
like that
for
as
sure.
well.
Yeah.
So I'm hoping that software guys will eventually be running this at a higher level.
At the library level, yeah.
But at the moment, yeah.
Okay.
At the low level is good.
Okay. So one thing we're going to need is we're definitely going to need to turn the robot on, and so we're going to have to power it up. And then we're going to have to figure out a way to talk to the motors. Now, I'll show you how that's done. These motors, again, you might not need to know how this is done, but these little white boxes are going to take the throttle signal, right? So we might define a variable called throttle or not or whatever, and the throttle signal is a bit strange in that, what would you think of as a stop command or a stop throttle? How much throttle do you put out if you don't go anywhere? You'd think you'd put out 0, right? Okay. We're going to put out 90. So we're going to talk to these as if they are 180-degree servos. So what you've got is 0 is full reverse, 90 is stop, and 180 is full forward. And that's just a way that Arduinos communicate over a protocol called PWM to motor drivers and servos and things like that. So if we're happy with what's going on this screen and we think we understand this screen, yeah, we'll go to the next one then. Okay, so now I've included another library called servo.h, and it's the thing that's going to help us communicate with those white boxes by generating pulses of the right width corresponding to how much throttle we want to put out. I've still got my metro, I've still got counts. I've introduced a variable called throttle. It's an integer, and I've done this. This servo command is something that is enabled through the servo library, and it sets up I don't know, Rex, what do you call that thing? This thing called my servo left.
It's pointer.
A pointer, okay. It sets up a pointer that has certain properties. So now we can write commands like my servo left dot right. So that now means something. It says write the throttle command to the servo on the left. Somewhere in here we're going to have to define that the servo is on certain pins. My servo left dot attach, so it attaches pin 4 to this servo. And now we'll leave that out of it for now. Okay, for So this bit I got from, all I want to do right now is check and see if we've got the motors running. And the way to check to see if I got the motors running, I've just used something called file. So in Arduino, you always build from examples, right? So every library that I've used, if I go file examples, so let's see, the first library we used, what was the first library we used? The Metro library, right. So I'd go down here to Metro, and I go serial interval. There's the code that I need. This is where I got all the code from. It tells me to include the Metro, set up the Metro, set up the serial, if serial Metro check, you just copy and paste this stuff. There's a couple little changes because there's some things that have expired, but anyway. The next library we had was servo. So I would go file, examples, servo sweep, and servo sweep gives me this command that says for throttle equals 0 to 180, throttle equals plus equals 1. So in steps of 1 degree, right to the left servo the throttle, and right to the right servo 180 minus the throttle. Why would I have done 180 minus throttle for the right one and throttle for the left one?
Because you wired it back.
If I have a motor sitting this way and a motor sitting this way, and they both turn clockwise under positive voltage, is my robot going to go forwards? I'm going to spin like this. So if I want this robot to go forwards, my left one needs to be flipped. And that's one of these things that your libraries can often handle for you is your left one will be, the throttle for the left one's always flipped relative to the throttle for the right one. Okay, so I'm going to put the robot on the blocks because it's going to start jumping all over the place. And I'll plug in the battery and wedge the battery in here somewhere so that it doesn't jump out too much. Okay. All right. So it's going to sweep from 0 to 180 and then from 180 to 0. So full reverse to full forward to full reverse to full forward, sweeping through that. Now, I have also done one thing that I didn't put in initially, and anybody can somebody tell me what pin 6 is being used for? I can tab things over. Let's see, this whole content is in that if statement.
Switch?
What for? Remember that 90 is a stop condition.
Start driving.
Yeah, or
Is the kill card?
yeah, now you're getting it right. So if 6 is low, what's going to happen? It's going to stop. So I think of it as an enable pin or an enable button. So normally you'd have that on the switch, and this is the enable switch or the kill switch. So if 6 is low, the robot shouldn't really go, although there are some issues with these delays that it's unable to check the state. It only checks the state of this thing after completing a full forward and back cycle, right? It's not checking the state of this very often. It only checks it, because look at all these delays. It runs this for loop for 180 times 15 milliseconds. Then it runs this for loop for 180 times 15 milliseconds. Then it goes back and checks the state. So there's some problems with that. But for now,
Put that on the neutral.
could do, but this was just, we're not going to use it this way. We're not going to use delays at all. So that's going to help. So let's push this, and then if pin 6, I think pin 6 is current. So I put this little wire in here that goes from 6 up to ground. Is it done uploading? Okay. So we'll see if I put this over. There we go. So let's see the direction that it's going. If you put my fingers on it, that's backwards. They're both going this way, going that way. Good. So that seems reasonable, and I can. If I switch this over, it's not going to die immediately. Yeah, unless you get it. Sometimes. You happen to catch it at the right moment, right? Any questions on? So we still haven't really started to do any control, right? We're just getting the robot operational, making sure things are wired up correctly, making sure that things are working. So now we've got motors that can spin. What would be what's our next step going to be? And we could, let's look at our encoders while we're doing that, actually. Let's see if we can still track encoders. Should dump new data every once in a while, but it has the same problem, I think, is it gets messed up by the delays as well. I think the delays are screwing up the metro, and so these two things have to synchronize. So we'll get rid of the delays on the next stage, all right? Let me kill that. There we go. Okay.
I noticed they're not exactly even, so does that mean it's kind of like slipping or?
Yeah, what we're going to see is that one side of this robot has more friction than the other. So if you increase the throttle, one will start moving before the other one,
Yeah.
because one got a lot more friction on it.
Is that by design or?
No,
is it-
that's just shoddy build quality.
Can it be?
You could put some work into it, and I think it's not a bad thing to think about is where's this friction coming from? Is there one belt that's a bit tighter than the other one, or whatever it is? But it can be, one of the things that can cause it is, on these motors, this is getting in a bit beyond for you guys, but I've seen it a lot where if you put too long a screw in the face, you bend the gearbox, and then you add a whole bunch of internal friction to the gearbox. It's actually kind of hard to see unless you do this thing of slowly increase the throttle and see when it turns on. But that's the very beginning of where it could occur. It could occur in the gearbox, and it could occur right up to anywhere down to the very last bearing on this system. So it can be a bit annoying. Okay, so let's go to the next stage if we're happy with all this. So we still want to make the robot drive to a certain place and then stop, right? So what are we up to, 4 now? Yeah, we're tearing through, okay. All right, what have we done here? We still got servos, we still got interrupts. We've attached that, yeah, it's all the same. We've got our serial, our metro check. Okay, so what is this doing here? Let's have a think about what these lines here are doing here. So the else is still shutting off, so digital pin 6 is still working. So if pin 6 is high, this is what we're doing. And we took out all the for loops and the if statements, or all the for loops and the delays.
This one's just checking to see if you've got the two position.
That's going to where you set it, right? Give it 1,000 if it's
Yeah.
more or less.
We're gonna do something a little drastic here. This is how I started. 180 minus. Okay, so now we're still, so what it's gonna do is, if our target position, so we've defined hopefully target position up here, yeah, so 1,000, so we're trying to get to 1,000. Every time we hit the reset, we're gonna try and get to 1,000. That's something that's that target position is something that in software or control, you're gonna have to give it. That's gonna change. You know, if you wanna move 10, then you give it a new target position. But for now, we've just said to go to 1,000. So if target position minus count is greater than 0, that is, the target position is ahead of us, hopefully, if we've got things wired up correctly, then we're gonna put the left servo at full throttle and the right servo at full reverse, correct?
I know what this is going to do. It's going to go apeshit. It's going to go.
It is going to go apeshit, yep. But let's watch it go apeshit anyway. So, because the reason it's going to go apeshit is if we go back to this, picture here. This is where we'd like to be, and as we approach that, as we get, even if we're 1 millimeter away from our desired position, we're still going full throttle, 100%. So we're always going to overshoot. We're going to blow past our target position. Then our computer's going to go, oh, you're on the wrong side. Full reverse, try and go back, and it's just going to, bang, bang. That's why they call it a bang, bang controller or an on-off controller, right? All right. Now, we are enabled, so this will probably, I'm going to have to kill this, I think, now we're on. All right, so I'm going to hit the reset. There it is. Okay, so that's it, overshoot. Right? Yep, that's the bang bang controller that's not happy with it. I mean, it's jumping back and forth around its target position, and we should be able to look at the serial monitor here. You can see what sort of values it is. It's not necessarily jumping by that much. Only 6 or 7 or 8, maybe 10 ticks. There's a 13 tick overshoot. More than we want, and it sounds awful, and it stresses things. It's going to vibrate things. Screws are going to fall out. We're going to drain our battery more because we're throwing lots of current in it all the time. We can get reasonable control doing this. If we're stuck with this control approach, what can we do to make it work a little better?
Drive it slower.
Let's just reduce these. So what's a number that's not full throttle? Yeah, I had it at 120. Let's go to that one. Yeah. And what would this one be then? 60, good. Yeah. And then this one would just change these. So you could define a variable that's like, you know, forward throttle or something like that. And we'll just make these. And then the 180 minus handles all that. Let's dump that. And in fact, why don't I get someone else to do the enabling? Someone else move pin 6 to the red rail. Remember that these breadboards are split down the middle, so I spent 10 minutes using this side of the rail and not figuring out, like, going through wires. Like, this wire must be faulty. So yeah, so just move that one to the red side. It still jumps a little bit, right? We might have to reduce it, but hit the reset button on the board. We'll repeat the process. So you can see they approach their value, still banging around a little bit. So not great. Let's kill that one.
You could probably, could you define it to say, like, if it's within...
Plug that in the blue rail. Yeah, you were going to say?
So if it's within... If it's within, like, 10 of, like,
Okay.
between 990 or
Sure.
1,010, like, just leave it?
Yeah,
'Cause
so
that's-
how about we do, yeah, so that's called bang bang with a dead band, or on-off control with a dead band. So you create a band where you stop, right? And so we could do that, right? How would we do that? We'd say if target position minus count is greater than, how about 10? And this is if it's less than minus 10? Is that what it would be, right?
Yeah.
You with me here? Let's go 10, let's go minus 10. Now we do need to put in another one that says to set it to 0, right? So you'd have to say, what are we going to write here? Well, we could put an else actually. But then each of these needs an else, right? You could do else if, else if, else.
Yeah, you could do else ifs, the whole, to make them all elifs or something, and then put
Yeah,
else
how
at
about
the
this?
bottom.
So make that an else if. Does it actually accept else if? It does not.
Yeah, space.
Else
Underscore?
space,
No, space. Yeah.
Oh, okay, cool. And then this then becomes an else, like that, and this would be, we get rid of the logic condition here, and we just put this at 90. We can just try that out on the left one, because that should just handle the left one, whereas the right one should still go screwy, right? Let's try that. All right, yeah, he's my dead man, on the dead man switch. So this, hopefully the left, now the front of the robot, this is the left on the front, this one's settled down, this one hasn't. So hit the reset button, we'll watch it again. This one is the one we want to see. Almost put some colored marks on there. Yeah, so the dead band's a reasonable way to do it. Really simple way to do it. Now, however, there's an even simpler way. Want to kill that for me, Tim? So that's what we call on-off control or bang-bang control. Yeah.
Just run that with a serial.
Yeah, exactly.
With a serial.
Oh, the window.
Oh yeah, sure. Hit the reset button.
Sure.
Let's see if it stops within 10. So the 997 is within 10. Sometimes it'll bounce once or twice to get there, but once it sort of finds any spot within 10, we could tighten up the control on that if we wanted to, but 3 ticks is probably pretty close. I guess you need to sort of figure out how much 3 ticks is and what precision you need and things like that. So that's fine for position control. For speed control, well, there's other things you can do. I mean, the problem with speed control is you need to maintain some throttle to maintain speed. So you can't shut your throttle off necessarily. If you do, it's just not as good. Okay, so where do we go next from this? Any thoughts?
You take the difference. You want to create a P controller.
Let's do
so
a P
you
control.
take the
Mhm.
difference of like target
Yep.
pos and count whatever, and then you use that as your.
Yeah. So what we've just done is what I like. This is the way I like to think of this. You've got. Let's call this our error signal, right? And that error signal is target position minus count. Okay. And we'll call this throttle. And I'm just going to go back to sensible throttle of +1 and -1. And we've just had if the error is positive, then we go forward. Although you could think of the signs as being negative, and so that was what we started with, right? That's our on-off control. Our deadband control was something like that would be our control with deadband, and the one we're going to have a look at now is going to be proportional control, where you have some line through the middle. And there's any number of combinations of this. You know, you can have proportional with a deadband. There's any number of ways to do this. So this thing is actually really simple to implement. And I'll show you how we do that. It's a one-liner. That's what's cool about it. Okay, so what have we changed here? Nothing there, nothing there. We still have target position of 1,000. We still go setup. We attach all this stuff. Okay, here's our loop. We got our metro. Okay. Now, this took me a little while to come to because you run into issues of float math versus int math. So now we're multiplying non-integer numbers and we're using non-integers. Now the Arduinos, many of you guys are software and computer type folks, right? And the Arduinos are simple, they're not MATLAB, right? And so if you take a number like an integer like 5 and you multiply it by a float, you might, or divide it by 6, you're going to get some weird numbers, right? And it's just, you're not going to get what you want. So I've done a bunch of things to fix this up. And again, this is one of these things that took me 20 minutes to get sorted out because all sorts of weird errors coming out. The motors were going backwards when they should have been going forwards, and anyway, all sorts of weird stuff. So what I've done here is defined a different throttle for the left and the right side, and that's a variable that gets recalculated all the time. This little bit here, any idea what's this doing?
Casting.
Yeah, so it's going to take the stuff on the right side and convert it to an integer. So if it's a number with some decimals in it, it'll convert it. And then I've used a decimal out front here, 90.0, to communicate the fact that I want it to do float math. So by putting a decimal out front, it's immediately going to put it in a mode that does float math. So it's not going to try and do ints. And then I've got this 0.8 as well. I've also put the 90 there because I need the center of this to be centered around 90, not 0. So there's 90 minus 0.8. That 0.8 is our proportional gain. Let's turn that way down for now because initially when you set up a proportional system, start with your proportional gain being really low, and then you slowly increase it until it starts to behave well, then you increase it more until it behaves badly, then you back off a little, okay? And now what I found with all this float math was that it worked great at low numbers, and then as I increased it at about 0.5, the whole thing went haywire, and you dig through and you dig through and you figure out, and you know, so I don't know for sure exactly why, but I eventually fixed it. So then we've got, so target position minus count left, we call that's our error. Again, it doesn't matter if it's speed, position, or temperature, you've got to have that number, that error number, right? And it's usually just a difference. So we're going to multiply that by 0.1. Let's just think about what it means. We typically are going to have error signals that are 500, 100, 200. So if I multiply that by 0.1, let's say it's 200, I'm at 20. That's not bad, okay? Then I'm at a throttle of 90 plus 20 or 110. That's a reasonable number, right? If I made that gain 5, it's a bit big because I can have an error of 500. Then I've got 500 times 5, 2,500 plus 90. That's not an angle that makes any sense at all. It's not anywhere between 0 and 180, okay? So, and then I've got a right one that is, that's probably why I had some, well, anyway. It worked anyway in this way, but again, these signs, the pluses and minuses, took a little work to get to. The other thing that was useful here was this constrain feature. So this throttle value could be a very large number, right? If I have an initial error of 10,000, if I want to go a long ways, then my error is 10,000 times 0.1, that's 1,000. 90 minus 1,000, it doesn't make any sense at all, right? So I've used this function here called constrain that limits it to being a number between 0 and 180. So if it's above 180, it forces it to 180. If it's below 0, it forces it to 0. Okay?
So that means that if you're 1,000 away, it'll just go to the max speed.
It's still going to go full throttle. It's not going to, yeah, because if you tell the servo to output a number like 5,000, I don't know what it's going to do. It does some weird stuff. And that's why my motors were often going backwards when they shouldn't have been.
So does that mean that it's basically a bang-bang controller until it gets to a...
Yeah, that's right. There is a limit. That's right. And there is a limit to the throttle that you get here. And so one of the things that happens when you're doing anything in real life, so that's really what you've got there, right? Your throttle is limited. So if you took your principles from 324, you generally assume lots of linearities, and this is suddenly a non-linearity that can annoy you. And there are also linearities like the total amount of current you can draw from this, the total voltage you can draw from this. There's all sorts of non-linearities that may put limits on it, but that's absolutely right. Okay.
Why did you constrain the right server to between 1 and 180?
Is it 1 and win? Oh, that should just be a 0.
Oh.
Let's put that at 0. Thank you. Okay. And then we still shut that off. All right, let's have a look at that one. Yeah, you want to do the enable? All right, so what's our steady state error on the right one versus the left one? So the left is the first one. Steady state error on the left is 69. Steady state error on the right is
98.
So probably our right one is the slower of the two. It's the one that's a little more grabby, a little less. So if we put this on the ground, let's see what happens if we put this on the ground here. I'm gonna grab that box gear. I think it goes this way. Oh, my feet don't get
Lift your legs just in case.
Okay, you see it do a little turn at the end there? Because one of them shuts off a little before the other one. And I think we figured the right one shuts off a little earlier, so it's gonna drag right as the left one keeps going a little further. Okay, let's try, that's a lot of steady state error, right? We haven't quite got there. Oh yeah, those grub screws have gotten really loose even though I tightened them up yesterday. That's all right, we're gonna move that. So,
run along the line so we can sort of see where it.
how crooked it goes.
Yeah,
Sure,
you know what I mean. Like if you use this line for reference, you can kind of get an idea
Sure,
of whether it's.
let's run that again here. So this one, it almost ends where it started because the, well actually the right one almost came on first because it went like that first too, didn't it? That's a
Yeah.
bit weird. Well, let's turn on the, now it doesn't want to come back because the control systems are fighting me, right? Like if I can actually, there's a bit of spring in it, right? It's going to go back. If I lower the gain, I can actually push it quite a ways and it'll fight me back a little ways. But if we want to make this drive a little better, what are we going to do? What can we do to make this tighten up those error values? Change the gain, right? So
Maybe
let's go.
0.19 or something.
Let's go to 0.2. Yeah, let's see what happens. We'll double that.
Wouldn't you change them to each other? Like one's.
Because they got different signs, one's positive, one's negative, I think it'll be all right. Although,
I just
I'm
meant to
surprised.
correct for that.
Oh, you could increase the gain on. Well, let's see what happens here. We'll do that fine adjustment later if we want. Is that?
So what do you read?
It's just uploading here. It's not quite there yet. Although I'm going to do it again because it seems to have hung. Let me just check our ports here. Might have to reset it.
I think
COM2, I got a bad.
I'm just worried about it being plugged, like it's live, and when you compile, it's gonna yank the USB cable out of the
Quite right.
Yeah.
It still gave me an error though, so hold on, let's just try this again here. Let's
Oh, is
kill
that-
that. It's
that
still,
is
the
weird.
latest code didn't get pushed for some reason.
That way.
Okay.
Just it needs to be on the. Yeah, it needs to be killed because otherwise it'll.
Yeah, it's gonna run away.
Jump.
All right, and I'll just unplug it and plug it back into my computer.
It's got a decent amount of force behind it.
Oh yeah, there's plenty of torque on these.
Try a different USB. They generally don't like being unplugged unless you unmount them.
So,
You've got to unmount it as a,
how do I unmount?
well, just the same as you unmount any extra, as any.
What, like this?
Yeah.
Doesn't
well,
show up
it's not plugged in yet, so.
there. I might have to restart my Arduino program.
Yeah, I think so. Unless you have another USB port.
I've got two in the back and I jump back and forth between them. Try this one more time.
That's.
Oh, we should probably, well, no. Try it one more time, then I'll have to. Okay, do you wanna, if we kill this, though, it doesn't kill it because we gotta, let's just power cycle the Arduino. Alright, and I'll restart my Arduino program too. Alright, you wanna plug that back in?
The USB.
Yeah. we are still not our enable pin is low, correct? Okay, we're good. Yeah, so you can probably hook up the motor and then pull the USB.
It's gonna shoot that way.
The gain, oh, hold on, I'm gonna go back to, we're at 0.2, so that should be okay. So our gain's still at 0.2. Could put it on the blocks. Yeah, go ahead, pull it out. Enable and then hit the root and enable. Here, I'll lift it up.
Yeah, I think maybe we'll just put it on the blocks.
Get out of
Yeah.
the way.
Then we're not gonna see.
Now we can do the reset. So this is at a gain of 0.2. It's a little straighter, it still does that turn at the end. And we'll have a look at our, if we put it up on the, let's put it up on the blocks and we can look at the the error signals.
You have a bunch of code at the beginning to self-calibrate the differences between motors.
You could, I
How
suppose.
fully it's been assembled.
Would be, yeah, you could potentially. I think the idea is, what you want to do is have a tight position control system on each side and just keep it in position all the time. So what you don't want to do is you don't want to send your proportional controller a huge move. You want to send it a bunch of small moves. Move 10, move 10, move 10, move 10, move 10, move 10, move 10. And then they'll both move at the same speed. And that now is what we call speed control. That's essentially speed control. Speed control in this case is, okay, so hold on, let's push 0.3 and we'll see how we go here. And we'll get the serial ports going on that. Okay, one of those doesn't want to go, does it? So hit the reset button. The left side's not moving. Why did it
But
squeeze?
it's still on.
Hold on. This side of this is no.
Oh, that's a bad connection. It's not
Where'd
grounded.
that- oh yeah. No, see how this little break there? See these blue and red lines don't go through? This whole side is not connected to this side. So you can't use this side of the rail. So this has to come over here. And this has to come over
shit.
here.
Oh, so this half in that half.
Yeah,
okay,
see the
sorry.
little blank
Yeah,
breaks
yeah.
in those? That's
Yep.
all right. So reset that again. So we've still got
And
that.
then you go
Yep, enable
on it.
that, but on the near side of the. Okay. So steady state errors are now still a little worse on the right, but good on the left. But if we get those both within, a few ticks of one another, then we're going to be fine. So we're going to do that by increasing our gain again. So let's go up to 0.6. So this is how you tune the P. And in a full PID controller, you still tune each value independently through a sequence of slowly increasing until something happens, and then you go to the next one and you increase, and then you do the next one and you increase. Okay, let's see, how's our serial monitor? Okay, so the left one looks good. It's less draggy than the right one.
Can you increase the right and not the left? So
Yep, but yeah, for sure.
Becomes
That's,
more
yeah, because of the amount of, you hit the reset, let's watch it again, and we'll just keep cranking them up until they're both working pretty well. Okay, so sure, let's try increasing this one. I'm going to increase this one to 0.7 because it's still working, and let's try increasing the right one to 0.8. Not bad, okay. Let's go even more here. 998 and 990, still pretty good. So no overshoot yet. And I would say you would normally increase them both until you get some overshoot. Until you get just a little bit of overshoot. But
And then
once you put this on the ground though, the whole amount of inertia changes, right? So right now it has very little inertia because it's just the wheels spinning. Once it's on the ground, the whole robot inertia will start to push it. So overshoot in this case might be, we might overtune it, right? Tuning it off the ground is different than tuning it on the ground. Serial port, as you go.
Right, so the PID has to be tuned, the P has to be tuned with a full load too.
I'd say all of them do, yeah. Okay, so looks like the left one's working great. Hit the reset button, let's watch it again. Pretty good, so we'll increase the right one a bit more. Does somebody else want to, Kieran, can I get you to give up your job to somebody else?
Sure, yeah.
Somebody else want to sit down and be involved in this, pressing buttons and pulling wires? Come on. This is a very practical class. If I had one of these for all of you, I'd give you all one.
It's a MasterClass for a reason.
Wow, mass, I don't know, but all right. Someone's got to go hit the reset button on that so we can watch it. No, come on.
I'll do it.
Okay, cool. So it looks like we're getting pretty close, but the left one's just overshot a little bit, right? Yeah, okay, so we'll increase this by, we could potentially put it on the ground and then reconnect the serial port, and it should still be putting out the correct data. So let's just increase this to 1.3, and then we'll run it once off the ground, and then we'll run it on the ground and see if it's any different. Okay. So we've got, run it again, let's see how we're doing here. So it looks like 0 and 2 is what we're at for, hey, that looks really good. All right, let's pull the plug, put it on the ground. See how it goes. All right, just hit the reset button. Pretty good. That one still starts, it stops just a little bit before. So the other thing we might want to do is if we got a really well-tuned system, we might be able to get it to slow down a little bit so that it doesn't come to such a screeching halt, because this is coming to a very screeching halt. Plug the port back in, and let's see if we can get new data on our errors. Ooh, maybe not. Well, let's kill this and reopen this. So, reconnecting the serial monitor. Oh no, did we just kill it? We just popped it off there. Gonna need a new board.
No.
Alright, I'll go get a new board. I've got one in here. It's okay, no, we've got I have to go get another,
It's just 4 pins, I just don't know which way.
someone will fix it later. I have to go get a new board. Ah, that's too bad. Should have had the thing facing out.
Actually, it came off pretty.
Nick, do you know where if Rex knows where another board is? Because that's not a Mega, that's
It's upstairs.
Do you want to go see if he's got a spare Mega he can lend us?
Rex can probably fix that.
Yeah.
There's four pins. They're just four. It's just
It's
basically
fixable, like, I
riff
agree.
it
Hey,
back.
some of you
like-
guys did the soldering, so
Yeah.
just quick.
It's not
all
even
right.
soldering. It's just a clip.
So that's sort of, where we get to with proportional control, though, that we can fiddle with that until we're blue in the face, right? I think that's part of how that goes. One thing that is worth considering is you can have a control system, this sort of control system that has a little bit of a deadband is useful where actually you want to have remember that this doesn't really move until you hit a certain amount of throttle. And you can take that up by having a control system that looks like this, right? So that if you want to go forwards, that is if your error is anything, you have an offset and then a proportional amount. And that's a pretty effective bit of control for this sort of system as well, where this represents the minimum throttle needed to get moving. And that's a way of sort of taking out that initial deadband. And that could be different on your left and your right, for example. And then they should behave a little more symmetrically. I don't know what we call that, but that's pretty effective for these sorts of things too. The other, and then let's have a quick chat about the other two things. So you can get a library for Arduino. There's a PID library, and then it sort of will do the integral and the derivative for you. But the if we did an integral, anybody seen the? Okay. So we've got our P, right? And this is equal to usually some proportionality constant Kp times error, right? And what's our D term going to be? And we've got an I term. Well, look at the I term first. I stands for integral, right? So we don't have an integration function in Arduino. So how do we do the integration on a discrete system like this?
Just add it.
It's just a sum. So all it's going to be is
KP previous
KI,
plus
yeah.
KP current.
Well, we'll go, error plus error old. Where the old error is the error from the previous round through the loop. Thanks, Nick. All right. Do you want to see if you can get us a pair of snips too, and some cable ties? I got cable ties here. We just need a pair of snips, and we can.
To cut the
Yeah, thanks, Nick.
Alright,
Okay,
cool.
so that's all it is. You have to create another variable to hold the old error every time through, you put the old error in, but there are libraries that will do all this for you, so this is what Rex is talking about, functional stuff. And what's the D gonna be?
The subtraction, like the opposite.
So this is, I think it's kind of profound stuff, right? Like, we don't have to do, derivatives and integrals in discrete systems are really simple, they're just subtractions, but they're subtractions across time and additions across time.
Fundamental theorem of calculus.
That's right.
It's
So
like
this is
fx
gonna be
plus x
error
minus fx.
minus error O. Okay? And each of these terms can be tuned. So the integral controller is, what's the integral controller gonna be good for? Anybody remember? Or anybody have any thoughts?
Damping.
So let's say that you had that, we had our, let's say we went back to the situation where we had a KP that was kind of low, and we had a large amount of steady state error, just sat there at 990 or 970. What's gonna happen to this term when, and we'll put this on here, then you would say your throttle is gonna be equal to the sum of these, right? P plus D plus I, probably plus
Oh, there's the
90,
cover.
because we've got this 90 offset, right?
Are you finding that right?
So initially, these two terms were zero. So if we had steady state error that just sat there, every time through the loop, it would get bigger and bigger and bigger and bigger, and it would grow until this got big enough to move it. So the I is really good
I
at
think I'll just wire it up
handling
first.
steady state error. It's
Oh.
getting rid of the last little bit of steady state error that you can't deal with. And if you just have an I controller, it actually works pretty well. You can just have an I
That's the
controller.
same
It's
thing,
not
no?
that
Same
bad. It'll
Mhm.
oscillate, right?
Why
But
work
everything
on-
oscillates. Every real control system.
Well,
It'd be better if
will
we put it
oscillate
this
a
way
little
as
bit.
well,
Depends
because
on
then
the
it'll just
cache.
rip out rather than ripping it off.
And so if we go back to, I'll do it this way. So if you want to tune a PID controller, you're looking at your step response. We've been looking at step response, right? And if you plotted the step response for most of what we're doing, we've been seeing things that look like this. That, or maybe that, or maybe that, or maybe we just started to see a little bit of that when we overshot just a little bit, right? We hit 101 or 1001 a couple of times, so we just started to get our P term large enough to get some overshoot. I would continue to increase that P term until we get a little bit more overshoot, and maybe even some undershoot on the back, but we'll see. You might not be able to get it because there's so much friction on this. Then once you get that, you add D in. And the D will slow you down as you approach, so that you'll still come up hard, but you'll slow down as you come in. So the D term will allow you to get there, just like you have a really hard, stiff proportional control, but it'll prevent the overshoot, because it'll start to shut off the throttle before you arrive, right, which the P term doesn't do a very good job of. So the D might be useful, and then you may or may not need integral control. It doesn't look like we need it, because our steady state errors look like they're really small. But you can still try some of it, but it's generally simpler not to just have like P plus D or P plus I, depending on the situation, and in some situations you don't. So the,
do we want to mount this backwards so that it doesn't happen again?
sure,
Because if the
you have to rewire everything, but I
Well-
would rewire it and then, yeah, I think you're probably right. If
You
you,
know
if
what I
you
mean? If
think
the-
you can rewire it, then yeah, let's mount it backwards. Is that the new
do,
one?
do you care if I just jumble the you don't have any color?
Well, no, yeah, but some of these, like those two green ones, right, you have to make sure they go exactly as they were in the new one. So that's the new one?
Yeah, this is
And it's
the
already
new
wired
one.
up?
Yeah, I'm
So
just
just
trying
spin
to
it.
turn it around.
Just
Yeah.
spin it, don't even, yep. So,
Got two on the red.
so does that, are you guys feeling like, what else do we need to do for you guys to get there? We can talk a bit about line following as well. And I've got a little line follow row to show you
These are the
what
ones
that
that
looks like.
These are too big.
But,
What about addressing?
Yeah, they look better.
What do you think of
So
the
you can get a
concept of
longer, like red and
accelerate?
blue.
Because
Yeah, right.
there's
That's
a
all
fair
we-
amount of inertia there.
Yeah, so how do
Everything's-
we get up to speed? So the
Actually,
way
that's
that,
pretty
right, and as you, so, quite right, if we have a system, we wanna actually do really good quality control,
Get a red
position
and a
control.
blue or a red and a
What
black.
we wanna
That's
do
efficient.
is
Try and find a longer blue.
never have a very large error.
Preferably blue or black.
And
or
the way
something.
we don't have a very large error, the way this is typically done is you send it small
one?
new
A longer
commands.
one.
And the way you
Green.
accelerate then is you send it
I guess.
slightly larger new commands. So let's say every 10 times a second you sent it a new position.
You want an orange one?
The first time you send it a small change, the next time you send it a bigger change, and then a bigger change, and then a
Yeah,
bigger change, and then a
maybe
bigger
the
change. And
orange.
that's how you do it, make sure that both the left and the right side accelerate at the same rate.
Okay,
Then
yeah, we can use
you could
those.
maintain a velocity and then you could decelerate. So typically, on something like the CNC and things like that, and whether it's the student one or the large one, it will move
Are these ones?
the spindle where you are, it'll move it
So,
where it looks like this. So this is what's called a trapezoidal move, where this is velocity,
hang on.
and this is time. And this is trying to go from position A to position B. So it ramps the velocity, holds the velocity, decelerates. That's called a trapezoidal move profile. So the CNCs will do that. Moving your robot like that is pretty cool if you can make it do that. But the way you do that is you have to send it these new position commands regularly. So you might have I don't know how easy it's gonna be with the Arduinos. Normally you'd have a whole computer controlling each motor, and that motor gets step and direction commands.
Orange one that we had.
But it might be
What is
possible
that?
with all the modules that is helping build.
So are you saying you
Yeah.
change the length of the step size or change the?
Well, you could either change the timing between the steps, so you send it a fixed distance to move at different rates,
Yeah.
or you send it a different move amount at a fixed rate.
Or what about changing the game?
I would leave, normally the way that it would be done is you would leave this as a tight control system that always keeps the system in position. That's its sole job, is keep it in position, in position, in position. And momentarily to be out of position as you're moving it. But you might have a function that says, that's a move function.
Yeah,
And the
okay.
move function
Okay.
will take
Alright.
position commands, and its
But
job
I
is just to
think it's
keep
good
it in
from your
position.
side, but it's not
and
good
you
from
send it
your-
in position.
What's
And
that?
that's how I
Okay,
would do
okay, all good.
your, yeah, now, you could send it, you could also think, if you can figure out a way to measure speed, so we're measuring position. How would you measure speed if you wanted to measure speed?
F of x minus f of x plus 1.
Well, you've gotta look at, the timing between these pulses, or the timing between a range of pulses. Like you could check 10 times a second or 100 times a second, you could ask how many pulses went past. Then you could
Can you take
say,
care of
well,
this
I know
one?
that 100 pulses went past in the last 10 milliseconds. But I think it's harder to do that across a range of motors and
Yeah.
things like that. There are, speed sensors that produce analog voltage for speed, but I think I would try to do a lot with position control. And, yeah.
Can you use the ticks?
Hang on, hang
Dude.
on. Stop.
Yeah.
Stop.
With
I need
You
to
might be
have,
able to
program
you have to
running
put your
time.
hand on that because here the batteries are there.
It causes the runtime from the
I
start.
can't really reach out.
So you're talking, so you got these ticks coming in from the encoder,
Yeah.
okay? And then if it's going fast, they're coming in fast, and if it's going slow, they're coming in slow. And then, explain to me your thinking again then?
Well, you can break it up into blocks and check how many ticks you've covered
Yeah,
over the
sure.
runtime of that block of
So
program.
one way that I have done that, I haven't had a lot of success with it, but I've had it does work, and it's how the CNC, one way that the MQ speed bike is done, is
Oh,
you
wait,
use the
no.
metro,
Wait a
and
minute, now
every
we
100 milliseconds, you ask how many pulses went past.
Yep.
And you know that that's happening then, well, it should be happening every 100 milliseconds. If 10 pulses went by, you know your speed is X. And then that becomes, then you use that in your error signal and say, am I going too fast? Okay, well, I'll increase the gain or decrease the gain. For speed control, I like an integral, because once you have zero error,
Yeah, exactly.
well, it doesn't actually, yeah.
I could do it, but it takes time. Okay, so
Yeah,
maybe
no,
I'll,
for sure.
maybe I'll mount it there.
And I've never used one, but, well, I would look into them for sure.
Yeah.
The other thing that the Arduino libraries will do,
Just
and I
put
don't
on
know if
loosely,
you
hang
should
on,
do it though,
what was the-
is you can send, so
We'll
remember we
do
had that motor,
Yeah.
This way.
and it had an
Exactly.
A and a B,
There's a better way.
and we sent this one to an interrupt.
I'll hold it.
You can also
Yeah,
send
that's
B
right.
to an
Better
interrupt,
go. Leave it. Better.
and then you get twice the precision, because you can trigger an interrupt service routine on A or B. It does mean you have 4 interrupt
We're using
service
these ones,
routines, and your computer processor is gonna get interrupted twice as often. So you've gotta decide whether you need that precision,
Can you just
or
turn
you
this?
need the compute time to
Okay.
do other things. You've got that one processor, and
inside.
depending on how
Because
many other things
batteries
it's
are
doing
here,
at
I
the
can't
time.
Wait a
really
minute,
reach
So
that.
you probably need to
Yeah,
think about
okay,
your
so
robot as being in different states, right? You sort of think of it as during this state, at this time, all I'm doing is driving forward. And if that's all you've gotta do for this, 10-second or 5-second period, probably okay to have 4 interrupts
Okay.
going and doing it all at once. But if at the same time you're driving forward, you're trying to do Wi-Fi communications to the base station, probably not a good idea. So I would think of doing one thing, and then another thing, and then another thing, another thing, and don't try to do
I
all
appreciate
things
it.
at once.
Wait,
I haven't built as complicated a system on Arduino as you guys are proposing to do.
What's the, if you just drive this flat out,
Mhm.
what's the expected
Max
pulse
speed?
frequency of the, no, what's
Oh.
the pulse frequency of the?
Someone got a computer? Check out how many pulses, somebody Google, the Andy Mark Never Rest 40. And we'll see how many pulses per revolution it generates. And we'll figure it
I
out.
believe it.
Because maybe an alternative is to have just a simple inline program that polls the state of the code is,
Mhm.
but make sure it's doing
So one way, there is a function in Arduino called pulse in, P-U-L-S, pulse in, and what it does is it measures the time that a pulse is high or low, whichever one you want. And so you could measure the time that a encoder pulse is high, and that would give you an indication of speed. So that's probably the simplest way to measure speed. The only issue is if you're going slow, and this pulse takes a long time, your code hangs waiting for that pulse to go low. So it goes in, the pulse goes high, it starts a timer, the pulse stays high, it keeps the timer running till the pulse goes low, and your code can move on. So there is a time cost to using pulse in. You can have it has a timeout feature that you might limit at 1/10 of a second or 100th of a second,
There we go.
and then your speed measurement isn't going to make any sense below a certain rate, right?
So that's what it's for time.
Okay. So you guys are, is that, other questions on where you guys think you need to take this and what direction you need to go with this information? Are you guys also following lines or no?
Yes.
Okay, well, let's cover line following in, because this is sort of, there's a bit of interest in that as well.
Oh, don't cut them off. Hang on.
No.
So the robot that I've got for this is sitting around here somewhere. And in that tub, guys, is a roll of black electrical tape. Do you think you could dig it out for me?
I don't think so.
The black?
Oh, this tub.
There's a roll of black electrical tape in the tub. It's
No,
gonna be hard to see me because of this whiteboard.
I don't think you've.
We'll put it up on the table. Actually. Well, yeah, I need a little edge to follow.
I don't think you've got any.
Follow edges in there too. The only issue is gonna lose it. Well, I'll just do it on the board and then we'll demonstrate. Okay. So this robot has a simple code in it that is simply this. I'll write this one. If brightness, so it has a
No good. Use your this thing.
It has a light sensor out front. Now it's key that this light sensor be out front of the robot. If you put the light sensor in the back of the robot, it doesn't work. And in fact, if you put the light sensor in the middle of the robot, it often doesn't work as well. So the position of this light sensor really matters in terms of the stability and the dynamics of this thing. And I don't know exactly how and why, and I haven't done any math on it or anything, but experience I know that if you put this sensor, for example, a long ways out or bring it back to the middle or past the back, there's a sweet spot for where that sensor should be located. Okay, so if the brightness is greater than, well, let's say 50 out of 100, okay? So that means you're on the white. And then what we do is turn left. And if brightness is greater than 50, turn right. Okay? So what that means is if you've got a
Arduino is meant to be less than.
Yeah, sorry. Thank you. So you've got an edge where it's dark on one side. Okay? The robot, if it's here, is going to turn to the right. So let's say that it's moving this direction. It'll go this way. If it's in the bright spot, greater than 50, it's going to turn left and it's going to go this way. If you try to go that way, it doesn't work, right? It runs away. So this thing is going to sort of go like this down the line. Doesn't go straight, it always zigzags. All line followers will zigzag. They'll always go, they're like little sewing machines. Now this is essentially, what control system would we call this? It's a bang-bang. It's a bang-bang control because we're in one of two states. We're either in the turn left state or the turn right state. You could certainly make it proportional, right? There's no reason you couldn't make it proportional as well. It works fine.
Yeah, couldn't you just feed it like 100 minus brightness or something? And then it's
Exactly.
gonna- yeah.
And or 100 minus brightness to the left motor, and 100
and
minus
just
brightness negative of that, brightness minus
50,
100 to the
yeah.
left motor,
Yeah.
right? And then that's the simple way to do line following. Just, remember that it's following a gradient or an edge. It doesn't follow a black tape. So if you put a piece of black tape on the ground, it doesn't follow the middle. It has no idea what the middle is. The only thing it can follow is the edge, the gradient, the difference between bright and dark. And if you try to do it too fast, it loses it. You can experiment with how tight a corner it can handle and all this stuff. But the concepts of proportional control or bang-bang control are still all the same. So let's just quickly go into the other room here and I'll show you what this thing looks like when it does follow the line. Okay, but an infrared sensor might be fine. I don't know what the tape looks like. It's something you're going to have to play with.
You don't know what it looks like in infrared.
Yeah, that's right. You can test it out and see what goes. So we could, I don't know. What do you guys want to do? We could potentially try to put a D on this, although has that got lights? Yeah, it's got lights on it. Don't know. We could crank up the. Yeah, the D might slow it down. That's not a bad idea. Why don't we put a D in and see if we can bring it in a little slower to its final position? I haven't done this, so This is gonna take some active participation to make sure I don't stuff it up. Have we tried this out to see if it works at all? We should check and see if it works first.
Yeah,
I gotta
check
push
the
new,
previous.
we'll push this code here.
Screen's
The screen's not.
Oh, my screen's gone dead.
Who's in T2?
Do I do power there or?
Yeah, no, here, I'll get it. There's a
Is
power
there
button
T2?
back here.
Oh my god. Seriously? I'm in. Oh, you're T2.
So, yeah, enable that and see if it goes, and hit the reset and see if it goes. I think we're a long ways.
Oh, no, sorry, I haven't done the,
Battery.
I did a safety, yeah. Just, it didn't, go ape
That's
shit.
good, no, that's good. Okay, good, eh?
Alright, let's go.
Come on, hit the reset, see if anything happens.
Did you write it?
What's this thing?
Oh, sorry, those are the grounds. I was
Do we need
gonna.
some longer wires on that one?
Yeah, I forgot to, because
There's a
we
long-
rotated the
So I got a 5 volt here, see if you can find a long ground wire.
long blue. Yeah, we had one set aside. Yeah, we must have forgotten to do that.
Come in closer, hold on.
I was trying to leave a bit of space for the, yeah.
Let's do
Believe
we
it,
don't
Reddit.
need to work in here.
This one, yeah. I changed this orange one as well because it was a bit short. Is that
Okay.
where it should have been?
I know. I don't know, what's the orange one?
It
that
was
looks
blue.
right.
It was blue, but it was short.
The one that I worry about is, okay, we got our servos. Correct. Do we have any I2C communication with this guy? We probably just haven't pushed any code yet, hold on.
That's, yeah, well, if you didn't upload it, it's not going to do.
That's what I did. Computer's gone dark. How did you guys sleep just all of a sudden?
It's alright, you can.
Oh no, we did a full restart for some reason.
That's right. Do you know what's going on with the TV?
It was on for a minute there, my computer went to a full restart for some dumb reason.
No. Yeah, they do that. It's just going to upgrade Windows 10. Do not read.
Yeah, weird. Full restart.
Hey? That was funny. I hope we got that on.
Did we get that? Good question. That's the right question to ask, isn't it? Did you get that on camera? Okay, tower runner interrupts 5, that looks good. Okay, push this. What's our gains at right now? 0.91.3, that's good. Come on. Do it.
Yeah, well, did you?
It's compiling. Not looking good though. Taking too long to compile. Oh. It's just gonna time out or something. No. Time out. Got nothing on the port.
Did you whistle it as well? I always do that. No, I do it as well. I did it as well. I'm like, that was like perfectly timed.
Oh, there's no port. That's not good, is it?
Doesn't sound good. Well, this one's brand new, so.
Yeah, I know. And we've got, that's, but why do I have no ports? Try another port. restart my whole computer again, aren't I? Well, sorry about that. Any other questions we could talk about? I'm supposed to store it up.
I have a question.
Yeah.
You probably talked about this already, but when you're doing the target position and the number of counts,
Yep.
how does the code know where the current number of counts is?
So that's the job of the interrupt service routine in a sense, right? So the interrupt service routine, we start it when we initialize it, we set the counts to 0. And the interrupt service routine, its only job is to either increase the number of counts or decrease the number of counts anytime a pulse goes by on the encoders. If you are only ever going to move forwards, if you're never going to move backwards, you could just say any pulse on the encoder should add to the number of counts that I'm at. And you're just counting, oh, pulse went by, increase the count, increase the count, increase the count, increase the count. Every time a pulse goes by, we increase the count. That's how we know where we are. But we do have this possibility of going backwards, so that adds in the other. That's why we need both the A and the B. Does that help, even if regardless of the A and the B bit, does that help explain how we know what the counts are?
Yeah.
We have a bit of memory in the computer that increases that or decreases that depending if we go forwards or backwards.
So I guess we're going to be calibrated by something. Obviously, we have to start in a known position.
Did we get a calibration on the motors?
No, I couldn't find one.
Couldn't find the number of ticks per revolution. All right, hold on. Let's see if we get a port yet for this. I still have no port.
We'll get your calibration.
What the hell?
Oh my God, you ended up doing this. But so we'll have to know our starting position pretty well, right? I mean, within a centimeter or something.
Is it possible that I fried something
Yeah,
and
that's
that
why I got so many.
pulled out?
You could have, you're using the same port on your
I've used
laptop.
I've used three different ones.
Is that output count per revolution?
Yeah, so I'll pull that up here in a sec. Let me just check and see if I have anything on COM 10 here. No, I got nothing. It makes the beepy noise. I think it'll be a driver issue with this. Is this exactly the same one? No, the other one was a genuine. This is a not, right?
It'll have a different driver.
Yeah, I don't have the driver for this one. That's a genuine Arduino, right?
No, they're both Mega 256.
No,
Does it say Arduino on it, or
we
is that a
don't
different
have-
name?
it's not.
Here it is.
Neither of them say I can't see the Infinity logo.
I can't really see.
Yeah, okay.
There you
So let me just, while
You
that's...
hold them next to each other. Well, come over. Like, if you hold them next, they've got exactly the same.
Okay, I'll look two things up here. We're going to look up an Arduino.
Well, it's
And
not genuine.
I'll look up.
But I don't
okay.
think this is either. Like, if you put them next to each other,
Yes, so they're not.
if you put it down, here, you just like you can see every part has it says CS4725B, CS16. I mean, they're the same.
It looks like the same manufacturer.
They're the same everything. Like even the component, like.
At the bottom.
Did you see something? Here we go, yeah. Output counts per revolution of output shaft. 1120. 280 rises of A.
Oh, it's a slightly different shape.
Okay, so that's the total number of pulses.
Oh,
The
well,
bottom
then
number.
I wonder why they've
bottom
got
number
it.
is
So I would guess we have
slightly
280
different.
pulses on A per revolution. So if we did, and I think that's directly coupled, so one output,
This is the chip.
so we were doing 1,000, which should be about 3.5 rotations of that wheel. That's about right, it seems, distance we were going.
What you have to worry about.
So we could set our,
Uh,
and they're 4-inch wheels, so we could do some calculations to figure out if we want to do exactly a meter, how many pulses we'd need. So that 4-inch wheel is about 10 centimeters, so a meter is 10 rotations. So we'd want 2,800 pulses to go one meter, I think. Although, no, we were doing more than that, weren't we? We were doing about a meter.
You did about a meter.
Hold on, let me
Meter and a
see
bit.
if I've got anything on here.
Ooh, a torch.
Uh,
Oh, that'll, yeah.
Actually, yeah, your phone's got a magnifier on it, so it's pretty handy.
Yeah, the camera.
Well, it just has a magnifier in it. Well, it depends on your phone.
Is that an R? Does it have an R number on it?
I was trying to look at the interpreter chip that connects.
ML Mega 16 V2 or U2. Yeah, they're the same. That Atmel chip is.
We don't know which rev it is though. I'll just take this. This looks like a driver file, right?
Where's the packet for it?
It's got nothing to do with it.
Well,
Yeah,
just too bad.
It's just a static green track.
Oh yeah, true.
That's all it is. It's not dusty.
The only difference I can pick up is that some of the numbers are written upside down.
Can you get a USB cable?
Hey?
When you ripped it out, the USB cable. There's some of them that could be bent or something. And the USB cable itself.
Yeah, maybe it's the cable.
Yeah.
Let's get
But
another
it
cable.
seems like the
Yeah, but the power's there.
power's on, yeah.
Yeah. Yeah, all right, open the box. I got another one in there. Doesn't look too bad, but you never know. It's good thinking, Aaron. There we go. See if that gets us over. No, it's still definitely not mine, but- Anybody been through this process recently? I haven't had to do this in so long.
I'm a bit confused because if it's running the other device, it should have the hardware.
Should have the hardware for it,
Can
yeah.
you, does the other device work? Yeah. Can you plug it in?
This one?
Yeah.
Yeah, I'm tempted to try that actually, because it.
Don't rewire, just plug it in and see if, well, yeah.
But if it's a, so the Arduinos that I get from China, they usually have a different FDI chip on them, so they use a different driver. But it's not hard to get the driver, you just have to, it just takes time. But it looks like the FDI chip is the same, I think.
I feel like they should have bought more than one.
Should I try this one?
Getting
The broken one?
Navigate and select the driver element.
Okay.
Okay, well, let me just move this to the drivers folder of this. Are you kidding me? No. What is it? This thing's supposed to have. There's supposed to be a drivers folder somewhere here. Which there isn't. Oh, it's totally cooking. Alright, well, our lesson may be wrapping up here. See if I should be able to. Why can't I navigate to this thing? Okay, well, I think we're done here. Unless anybody wants to try and help me fix this crap. I feel about the drivers. Same things. Okay, I think we're gonna leave it unless someone wants to fix this, we're done. Unless there's other questions we can talk about from a theory perspective or something. But the only thing I would say was, I think putting a D term on that might allow it to approach its target a little smoother and not overshoot, not come to such a hard stop, while still having a small amount of steady state error.
Is that going to make a big difference though? Because I suppose you don't want the cans flying everywhere.
Yeah. Plus, if you want to go to a position and then stop, but you could also have a tight control system, but limit the total speed. So we're allowing the control system to use its max throttle, but we could still have it as a high proportional gain, but not achieve max throttle. That might help a little bit, but yeah, I don't know. The other option is sending it regular updates to position so that you can decelerate it as it comes in by sending it a move profile, essentially.
What if you had something like?
What are we plotting here?
So it's like a proportional with like an 80%, and then if you're way out, you can.
Yeah, I mean these things are not crazy, and then lots of these things can be tried and worked on.
You're just making this up.
Yeah.
I mean, yeah.
Are you allowed to have an actual curve on your graph there for the deceleration, or does it have to be a proportional straight line?
Well, remember that's not deceleration. What that's putting out is the voltage you apply to the motor, and that's not equal to speed, right? That's equal to sort of more like, I mean, it is in a sense, it's by the time you get to steady state, it is equal to speed. If you double the voltage, your steady state voltage should double. But the dynamics of how you get to a speed are governed by the torque speed curve of the motor, which is sort of linear, but it's got all this friction in it as well. You can have any sort of control rule you want, and it's not crazy to fiddle with these sorts of control rules. And there are lots of custom controllers you can make and things like that. And just that, the idea of a proportional control with an offset to overcome that initial friction is a good example of a custom controller that's specific for this system that might work for you. But yeah, there's really any range of things you can try. And you can spend a lot of time buried in trying to tweak something and get it to work. And the sort of fix to that is have a tight control system that is only meant to make small moves, and that should help fix that problem, whatever it is. But you certainly could, get out the PID library and spend an hour or two just tweaking those parameters until it works. But look up, if you're going to use the PID library, look up and read about a PID tuning protocol. So there are protocols for tuning PIDs. I mean, PIDs represent 90% of all the controllers in the world, and there are plenty of people who know how to tune them, and there's procedures where you turn this until this, and then you turn this until this, and then you turn this until this, and then you're done, right? If you don't follow that procedure, you got 3 parameters and a large parameter space to explore, and you will be there for hours. Yeah.
I just had a great idea when you were doing that manually.
Mm-hmm.
Arduinos can read turn plots really.
Yeah, absolutely. You could literally put a PID turn plots on. Mm-hmm. It's not that much harder to do it in software, but certainly you could. Where you hit the reset, adjust, hit the reset, adjust, hit the reset, adjust. Yeah.
It would make it easier to do it, like you wouldn't have to reconnect the USB and find the device.
Yep, correct. You wouldn't have potentially this problem. So yeah, that's right. Most PID, off-the-shelf PID controllers have 3 little turn plots, one for the P, one for the I, one for the D, and you do exactly that. You run it, and you typically even look at some sort of step response or something, or listen to it, or things like that, and you adjust the P, then the D, then the I think is how it goes.
Yeah, so
but look up a protocol.
We might have 9 things. We could have left motor, right motor, and then the correction for the line tracker.
Well, you might have to tune the left and the right independently, but start with them being the same. And then the motors, there shouldn't be that much difference. If it's the same motor, it depends how much load it is. But once these things are geared up a lot, the load doesn't, it's not. With the 6, is this a 40X gearbox? I don't know. Once you've got big gearboxes, things become easier to tune as well. Like we didn't work very hard, and we were getting, just with a P control, we were within a tick or two the first time, every time. The only issue is we were probably skidding a bit when we came to a stop, which is bad. You don't want to slide, right? If you're using wheel encoders, what you can't have is wheel slip. If you're going to use an ultrasonic or a distance sensor, then wheel slip doesn't matter. You're going to use your motors to get yourself in a position as well. That's another thing we could have demonstrated with that robot, is it has an ultrasonic sensor in front, so you could drive this into a wall with a P controller, and it would drive in and it would stop some distance from a wall, which is similar to, I understand how many of you guys are going to work. You're going to have some distance sensor bounce off some wall. potentially.
We were until you told us to keep it simple.
Using encoders on the wheels. Well, this seems to work pretty well. I mean, I think that, you know, we could probably run that system over and over again quite a few times, and it's gonna work. Until eventually it starts to drift and twist, and then you lose it, right? But every time you have wheel slip, you lose it.
Can I go to
Yeah.
intro with the
Oh.
anything else?
Well, I gotta, yeah, why don't you see if you can talk to that anyway? Isolate it to my computer.
Slam the brakes.
So I'll put these bits of Arduino code up. I'll give them to Rex, and he can make them available. These little 5 stages of this software.
No, there's something wrong with the Arduino, I guess.
Yeah.
You're getting the same error.
Because that slows you down the
Okay.
testing process. We put 3
All right.
terms.
Any other questions?
Put 6 or 9,
Okay.
something.
Thanks, Dave.
Yeah. I wish I knew why this guy was giving us grief here, but. Okay.
Pull the plug on it.
Oh, what you mean, what are they doing? If you can find someone.
Oh, yeah. So you need to get a new, yeah, you need to get a new block. All the little strips got pulled out of the USB connector. So I don't know if the solution is a longer USB cable or a shorter one. Might be the shorter. Yeah.